Hello, everyone. My name is Nathaniel Harmon. I'm working on writing a proposal that aims to study large power generators, specifically cooling methods that are present in the rotor windings. The reason I chose to do this is that for these generators, there's a few limitations that are present throughout. The big ones that immediately come to mind to me are one, the excitation system. Um, these are limited in the voltage that they can put out, which in turn limits the current experienced in the rotor windings and basically reduces the strength of the magnet that is the strength of the magnetic field that is produced by the rotor, which again limits the power for the total generator as a whole. Uh, the next set of limits that come to mind are thermal limits that are experienced by both the stator and the rotor. Um, Both of these have uh, areas of improvement, I guess you could say, or needs of improvement. But I primarily work with rotors, so I chose to study the effects of cooling in these rotors. So what you'll find with these is that there's generally uh, two ways to cool these rotors. That would be either air cooled or hydrogen cooled as the cooling fluid. There are some that use water, but there's other challenges that are presented when you try to water cool a unit. Um, with this, there's typically on smaller units, what you'll have is a two-pole unit, which means that it is basically like a normal magnet. When you think of a magnet, you'll have a north and a south pole, and what those poles are uh, there would be a pole here, like this set of windings here. This is a rotor that's being built, so this set of windings will continue to arc over, and then there'll be one here that arcs over, and then there'll be another set down here that arcs over, and they'll go the other way. Um, Kind of counterintuitively, the poles are where the split is, like meaning that this loop here is not a pole. This is like one half of the North Pole, and then the South is here, and then North and South there. Same kind of concept on the four poles, except it's doubled. So instead of having a top and a bottom, you would have a pole in all four quadrants. Um, so those are the general ideas of the rotors that I'm going to be studying. Um, it's possible to cool these rotors, um, what we call indirectly, which is if you can imagine if you had a solid piece of copper like this, you would just be blowing a cooling flow over the top of it, um, which in some applications, especially at low power, is fine because at the low power ratings you're not generating as much heat. But with this, what you'll find is that, um, as you might imagine, the coldest side is going to be the side that's exposed to the cooling fluid. So you'll have a non-uniform temperature distribution, generally from the top to the bottom, top being the coldest, the bottom being the hottest. Um, Other methods are what I'm focusing on, which is directly cooled, which means that we are directly passing the cooling medium into the rotor winding itself. And so with that, there's really two ways to do it. Two main ways that are common, and that's with radial cooled, which is pictured on the right. And so air cooling air comes in through the subslot, and then it gets passed up radially outward through this channel in the middle, hitting all the copper as it goes, and at the top. The other option is axial cooled, which is each copper turn has a vent in the inside. It's these little squares that you see in this kind of middle picture, the right picture with color, and cooling air gets passed either into the page or out of the page, whichever, um, and that cools the windings internally. So these are going to be the two main focuses for me: is air and hydrogen cooled, and radial and um, axially cooled. So with this, what you'll find in a lot of generators, not just specifically two pole or four pole, even though a two pole is pictured here, is that there's a non-uniform temperature distribution. Um, you can see that in this top picture. The scale is kind of off, but red is hot, blue is cold. And so The reason that this is important is that uh, these windings, if you notice, between each layer have a turn insulation that basically insulates each copper piece from the one above or below it. And so those have a rated temperature that they are that cannot be exceeded. So in the case where we get hot spots, you can exceed that temperature, that insulation will degrade, and you can fail the unit, sometimes catastrophically. The other reason it's important is that because for every 10 degrees you increase in the operating temperature, the lifespan of that insulation is halved. So generally you're operating maybe like around 120 degrees, maybe a little higher depending on the rating of the unit. But if you go 10 degrees higher, you cut the insulation life in half, which means you have to come offline to fix it. Is one outcome. The other outcome is that in this case, the middle of the unit would have their insulation degrade faster rather than the ends, and so you'll get wasted material, essentially, material that was not used for its full lifespan on the ends. So that's kind of what I'm trying to tackle. So some research has been done, which you can kind of see in this table, is a lot of stuff. The B, C, A, and D are all different factors of, we'll say, like pressures or vent sizes and things. The one I want to highlight is this minimum value HTRW, which is the minimum highest temperature of the rotor windings, and that is most heavily influenced by this factor C. And in this C, or in this research that's presented here, C has to do with the width of the vents. So it has to do with the surface area of between the winding itself and the cooling flow. So the goals of this project is I want to try to understand the factors of how we can increase this cooling besides just a more contact area equals better cooling, because when you're increasing the contact area, there's some trade-offs, mainly in mechanical stresses. As if I go back to this picture here, if I increase the size of this square, this whole system is rotating, and then I'll lose mechanical strength in the windings itself. So you can't go too far. But that's mainly what I'm trying to accomplish, is that, and try to keep a more uniform temperature distribution so that we can combat what I was saying with the wasted materials, or the wasted materials on either ends, and just operating in a region where you're not cutting the life in half. Second to that, I would like to develop a system that can take the operating parameters of these generators, and I can feed that into a model that can then alter the geometry to best handle the temperature loads. And there's ways to do this. So it can essentially give it a 3D model, and you can manipulate that 3D model to optimize towards some parameter, which is in this case going to be minimizing the temperature, or the difference in temperature to try to keep it more uniform. So the task that I have is going to be to develop a numerical model through the use of fundamental fluid flow and heat transfer laws, coupled with machine learning for optimization and CFD for final verification. So we'll get a little bit into the machine learning stuff later, but essentially it's going to be using all the equations that my air friends know and love, to calculate fluid flow and heat transfer. Step 2 is going to be to link these multi-physics simulations and performance sensitivity analysis on the models and deploy machine learning algorithms to optimize the system based on a set of constraints and objective functions. What you can see here is a program called ANSYS OptiSlang, and this is just a random example, but with this what you can do is I can give it a model that can do FEA. It can do it can link into Fluent to do heat transfer analysis, or CFD or whatever, And additionally, I would like to link it to ANSYS Maxwell to also evaluate the electrical properties. So you can kind of perform a sensitivity analysis on all three of these systems, but it's kind of acting as if it is a single system because the results of one are fed into another. And through the use of the machine learning techniques, you can figure out the interplay between input parameters of the fluid and the geometric properties of the winding itself. This is kind of a second step to that. Again, you can see that's basically what they did in this research is they're trying to determine in the middle the order of influence of the A, B, C, and D factors and what output parameter they influence the most. If you're familiar with sensitivity analysis, that's basically one of the steps is what I'm trying to do here. The final step is I would like to not acquire a generator, but acquire the ability to outfit a generator with some sensors, do some testing on it based on like take measurements of the inlet temperature or the fluid temperature at the inlet, the pressures, densities, that kind of thing, as well as measurements of the windings themselves. And then I want to feed that back into the model and then say instead of optimizing, just do a simulation and tell me what my outputs would be. And by doing so, I can compare the system output and the real world test data and kind of get a sense of how accurate this model is going to be. So the broader impact of this is one, we're going to be enhancing the power generation's reliability. So companies will be able to operate longer. They'll be able to make more money, hopefully, because they won't have to come down for maintenance as much. And who knows, fingers crossed, I'm hoping that in that case, we'll be able to lower electrical costs for people that use electricity in their homes because companies wouldn't have to be paying for as much maintenance and outages and upgrades and repairs and things. So we'll see. Also, this simulation framework that I'm trying to set up does not necessarily have to just be for these units. It can be for pretty much anything. So any system that has physics can kind of benefit from this. And then again, cross industry impact. So that's kind of what I was talking about, where it doesn't necessarily have to be this field. It can be literally anything. And so that's my presentation.